Hello and welcome to our webinar today presented by Dlubal Software. Today we will be working in our finite element analysis and design software, RFEM. The topic for the webinar today will be AISC Advanced Steel Design in RFEM. My name is Amy Heilig. I'll be the presenter today. I'm the CEO of the U.S. office. I'm also technical support and sales engineer, and our office is located in Philadelphia, Pennsylvania. My colleague Lucas Sunel will be the moderator, answering all of your questions that you go ahead and type in today. He's a product and customer support engineer, and he is located in our Tiefenbach, Germany office. I just want to let you guys know you can go ahead and show or hide the control panel that popped up when you logged into the GoToWebinar if it does seem to get in your way of viewing the presentation. We also want to encourage you to ask questions during the webinar. You'll use that chat option dialog box here, and we'll do our best to get to all the questions, but if by chance we don't, I'll certainly send you an email. With that, I think we can go ahead and jump into the webinar content today. So we will be go ahead and modeling beam and surface elements in RFEM. I want to show you guys the automatic finite element meshing capabilities. I think that this is a really strong point of our software. We'll also go ahead and do an elastic and plastic analysis and design. With the plastic analysis, we'll go ahead and showcase some nonlinear materials. And then we'll take a look at local buckling modes and imperfections, and we really want to relate this to the AISC code and what is required within these standards. So you can see here on my right is a typical frame type structure. You'll notice that we have, though, a very slender tapered column here and maybe a little small section of a tapered beam. So this is a little bit out of the norm of what you would normally encounter when you're just designing typical frame type elements here. So what we want to do today is to really focus on this connection area between the two tapered members. And instead of doing a 1D member analysis, we're going to go ahead and turn these into surface elements to do a finite element design. And for those of you that are not familiar with our program and how it's set up, I just want to briefly explain this. So RFEM is our main program, and that's showcased right over here in this picture. This is where all of your modeling, your loading, your finite element meshing, and then we can go ahead and perform an elastic analysis. This is all done within RFEM. Then we work on the add-on modules, and for instance, RF Steel AISC, this is an add-on module for member design per AISC code. We really won't be spending any time in this code today, but it's fairly self-explanatory when you're looking at our other codes that we will visit today. RF Steel is going to give us a stress analysis for our steel surfaces. RF Mat and L, this is an add-on module, but it's not something that we can physically go into once we're in RFEM. What this allows us to do is just to release these nonlinear materials and make them available in RFEM so that we can go ahead and perform a plastic design. RF-STABILITY is a stability analysis add-on module. This will give us our local buckling modes that we'll go ahead and calculate according to our design loads for our frame elements. And then RF-IMP will actually take these modes and go ahead and scale them and create an imperfection. Then after this, we take it all back into RFEM. So that was probably a little bit confusing, so I kind of just wanted to lay out our exact design process today. We will first start off in RFEM, and here we're just going to go ahead and run a linear analysis with linear elastic materials. Then utilizing the add-on module RF Steel, we'll go ahead and do a stress analysis to get our ratios of our design stresses over our limit stresses. Then utilizing the add-on module RF Mat and L, we'll go ahead and run a plastic analysis in RFEM as well. Then we want to take a look at RF-STABILITY, and like I mentioned, this will give us some local buckling modes according to the applied design loads that we have. Then we scale these local buckling modes to create an imperfection, and then finally we end up back in RFEM where we take that scaled imperfection, add it onto the design load to run a nonlinear plastic analysis. So according to these pictures up here, just to briefly point these out, I mean, this is just a simple linear elastic solution that we'll go ahead and run first in RFEM, and then we'll go ahead and find those local buckling modes, scale them, and lastly, we'll end up in RFEM to run our final solution. So with that, I think that we can go ahead and jump into the model. So this is RFEM itself, and I know that some of you are not so familiar with it, and some of you are, but just to briefly lay out what you're looking at exactly. So of course we have the graphic display here in the center, and then we have our tables down here for data input, and also our results are available in tables as well. Some people prefer to work in tables. And then a third option that we have that maybe some of the other software doesn't is our project navigator. You can see down here we have a data tab, a display tab, views, and after we want to run a result, we'll go ahead and get another tab called results here. We'll be using all three today, but you will see me in the project navigator quite a bit as well. So to save on time, I went ahead and started with a couple beam elements here. If I go into my wireframe view, you can see that these are just 1D elements. They're modeled according to their center line. They're connected at their center lines. So we can go ahead and render them here, and the program's going to give us a visual display, of the properties that these 1D elements have, but keep in mind that they really are just center lines in the program. If I go ahead and double click on this member, you can see I defined my tapered section with the member start as a W10 by 49. Now I defined my member end, however, as a different section. And what I did is I just simply took that W10 by 49 and I increased the depth to 20 inches. The material is steel A992, linear elastic material, nothing too special there. And then as far as this other beam up here, I can double click on it and see that I have defined it as a W12 by 53. It doesn't have a taper effect right now, so we will go ahead and model that as well. I can go ahead and select my beam members, and one thing that I really advocate about this program is a lot of AutoCAD-like features. If you drag from right to left, everything that is touching this graphic box here will go ahead and be highlighted, and if we drag from right to left, only the features that are within that box will be highlighted. So we want to go ahead and highlight both of these, and a unique feature in RFEM is that here you can see that we've selected lines, members, and nodes, but what I want to do is to hover over this member option, and we can actually generate surfaces from members. So now you can see that we now have 2D elements generated. We went from our 1D member elements to our 2D surface elements. And the great thing is if I double click on this web surface here, the thickness is 0.38 inches. Well, this was taken directly from my W12 by 53. So I don't need to worry about modifying the thicknesses, maybe the widths of the flanges, the depths. Everything is taken from that 1D element. So that's pretty useful when you want to transition into a finite element analysis from your 1D members. Now, I want to quickly just clean up the model a little bit. The program went ahead and created an FE mesh refinement that I'm going to delete for right now. We'll get into that later. And you'll notice here that we have a line, a dotted line here. If I double click on it, this is my 1D member element. It's now of the type null, so it's not going to be considered in the analysis. You can certainly leave that in there, but for me, I'm just going to go ahead and delete it. And because every member is consisting of a line underneath it, we still have a line here that we can go ahead and delete as well. I'm going to do the same for this upper beam here. Now again, like I said, the AutoCAD-like features, I can drag from right to left. It will select all of these nodes and the beam element. If I hold down my control button, I can go ahead and select these nodes in here. So only this upper beam is selected. Now what I want to do is I want to go ahead and move this beam down so that it's flush with the top of the column. And rather than using our move and copy tools, all that I need to do is to go ahead, select this center node here, drag and drop it, and now you can see that everything's flush. And with the use of those snap tools, the program knows that I want to snap to this center node. So very useful, again, when you don't want to utilize these copy and move features using this button up here, but rather just drag and drop. So a very quick way to go ahead and move those. Now, the other thing that we need to do is we need to create a taper-like section for this beam element. If I go ahead and select these 3 lines of the inner flange and I'm holding down my control key, I can right-click and I can create node on line. Now, I can either choose n intermediate nodes or a distance. I'm going to go ahead and choose a distance. Now, you'll notice when this dialog box pops up, I get all these black arrows, which are nice because this tells me at which end does my line start and which end does it go ahead and end up here at the top of the column. So we can see that these 3 lines begin at the bottom and they end at the top of the column. So therefore, I want to create a node 1.5 feet from the top. So you can see this node was added here on the line, but nothing else has really changed. Now, holding down the control button again, I just need to highlight these nodes and then simply drag and drop. You can see that the program snaps to these nodes I just created, and we have a taper-like section. A leftover node was up here. I can just go ahead and delete that, and we have our 2 elements. If I go ahead and I right-click on one of these surfaces and I say turn on my local axes of my system, now this is something that I really want to point out to you guys, and this isn't just in RFEM, but this is in most finite element software. You really need to pay attention to your local axes. So you can see here that my local axes are kind of going in every which direction. If I zoom in here to my inner flange, these 2 surface elements here, I have my local y-axis pointing up here, but it's pointing down on the adjacent element. This is a problem when we're looking at our results. If I were to view my positive y stresses, well, it really wouldn't be relevant in the case to view the results because the 2 surfaces have different local axis directions. So that's why we need to take careful note that all of our surfaces have the same orientation for the local axes. So one quick fix to this is I can just select this surface, right-click, and then there's an option called Reverse Local Axis System. So now you can see that the 2 flange local axes line up quite nicely. We can do the same thing for this flange over here, and now all 4 of those flanges are going in the same direction. And one thing I quickly want to do, because I want to discuss the surfaces up here in the YX direction, in the YX plane. I want to go ahead and draw a couple other surfaces up here at the top of the column and at the end of my beam. And to do this, I'm going to go ahead and turn on my grid, and I just want to quickly change the plane. If I zoom out, you can see my drawing grid. And then I can change my origin with just the click of a button. So I'm just going to set that here. What this allows me to do is just to draw my surface elements in one plane. It just kind of keeps me from clicking on some point way out in space and getting a very odd shape. So you can see here to draw a surface, we have quite a few options. You know, you have your typical rectangle shape, but then you can get into much more complicated type surfaces that, again, the program will automatically mesh in the program. So for here, we'll go ahead and choose a rectangle. Now, we'll just stick with steel A992 for this example, but the thickness, we want it to be 0.5 inches. So the only thing that I need to do is just to snap to these 2 points, and you can see that I snapped a little bit further out. All I need to do is just to grab these and pull them back in. And we need to do the same thing. Oh, it looks like I missed this one up here. And we need to do the same thing now for this end plate here. So I want to go ahead and change my work plane, change my origin, and then go ahead and pull up this new rectangular surface. It remembers all of my settings from previously and then just snap from one end to the other. You can see here that I have this panel displayed according to my surface thicknesses. Now, this is useful just to see, you know, the different thicknesses, as I mentioned, for all of our different elements. This is controlled under our display tab down at the bottom. You can change it to whatever you would like, but right now it's set on surface thicknesses. Okay, so now that we have all of the surfaces drawn, I wanted to also note to you the local axes of the surfaces in the YX plane. If I were to use that same example of reversing the local axes system, well, now we can see that the z-axis is pointing down, but the z-axis is pointing up for this upper flange. So that won't work in this situation. So what we need to do, and this is a very useful feature for when you have a lot of surface elements and you want to go ahead and change all of the surfaces, local axes at once. I just hold down my control key and select all of these. Now I right click in the surfaces and I click Edit Surface. And this is my surface dialog box. Now you'll notice that we have this tab up here called Axes. This is our controls for our local axes. So here we have the option we can do an angular rotation of our axes. For this example, I'm going to choose this option here. So what this will do is it will actually set all of my local x-axes parallel to a line that I choose within the model. So the first thing that I need to do is I need to select the line. And I just simply select one of the lines in our structure and I hit OK. And now you can see that all of the local x-axes are lined up with this particular line. So again, this is very useful for when you have a huge model, you have a lot of surface elements, you can select them all at once and change them parallel to a single line, and the program will automatically set that up for you. It looks like our two surfaces in the ZX direction are facing the same way, so we are okay there. I can right click, I can go ahead and turn off those local axis systems. Now the next thing we want to do is to go ahead and apply supports to this structure. And I want to start off with a new line support. And the default within RFEM is hinged and rigid. Pretty self-explanatory, and I think for this one we'll just go ahead with a hinge pin type condition. Again, I can just drag and drop and we see these line supports here. We can also right click, we can increase the size if we want, we can decrease the size, you can change the colors, so you really have a lot of control over the viewing options here. Now the next thing to do is to go ahead and apply some nodal supports. So realistically, this column and small beam section are part of a larger frame and inevitably a part of a larger structure. Most likely we'll have some purlins framing into here, preventing a lot of the Y translation. So instead of modeling the rest of these members, adding more finite elements, that'll really, make our analysis a little bit slower when we're adding in all these other elements. It's just easiest to go ahead and apply a nodal support in the Y direction. I want to go ahead and add a couple nodes while I do that, and I can just right click on this line, create node on line, at N intermediate nodes. Here I just leave the intermediate nodes at 1 and the program will automatically create a node there. I want to do the same thing for the center flange. Create node on line and intermediate nodes 1. Okay, so with the nodal support we go ahead and click on this option. And the default is hinge rigid, and then we have some sliding options. I actually want to create a new type here. And the options that we have here are translation and rotation. And if we want it as a fixity, we simply leave it checked. If we want it free, we just leave it unchecked. So that's just the basic simple pinned fixed or free. But we also have the option in here for quite a few more nonlinearity effects. So, failure if you're reaching a certain load, partial activity, friction. And what's great about RFEM is that you have the ability to really, get really in depth in your analysis in terms of nonlinearities and really wanting to have a completely accurate analysis down to these, small details. But the nice thing is that you don't have to sift through all of this information just to get to the simple fixed or free. Everything's kind of hidden behind the scenes, and that if you want to go ahead and get into these further details, then that option is available. But for us, we just want to simply keep this fixed in the Y translation direction. So you can see here I have a new type of support. I click OK, and now I can just simply add these onto the nodes here. So we'll assume that, again, we have some purlins framing into here. I'm also going to add one at the inner flange here to prevent torsional activity. Now, because our global axes are set up in the way that they are, it seems that these nodal supports are maybe a little bit in the way of our modeling. So under this display tab in our project navigator, again, this is everything that's going to control what's in our graphics window here. Has nothing to do with data input, it's just purely what you're seeing over here. So I'm just going to go ahead and turn off my nodal supports. They're still there in the background and will be considered for the analysis, but I just don't want them to be in the way of the modeling for now. Okay, we want to apply loads now. And, you know, realistically, again, this is part of a bigger frame element. We'd probably have some type of line load on this beam element here that would go ahead and distribute to this tapered beam element here and then into the column. So for us, we can just go ahead and apply a point load here. Now, keep in mind that when you have 2D surface elements and you just apply a single point load to one of these surface elements, you're going to get a singularity effect. I mean, there's no load distribution except for on this single little tiny point here. So you're going to see extremely high stresses at this location. So you want to figure out a way how to distribute this load realistically. And for us, we're just going to go ahead and distribute it through the depth of this beam element here. The depth is about 1 foot, so we'll just place a line load then along this web of the beam member. And maybe we're trying to find out, you know, what is the max load that this system can handle. And we certainly could put in our line load here and keep adjusting it, you know, double clicking on it, editing the magnitude. But an even better way is to make use of our parameters. Now, I've gone over parameters before in a previous webinar, but if you aren't familiar with these, a parameter is nothing more than a variable. So for us, we're going to go ahead and call this design load. And we need to give our variable a unit type. So you can see here that we have many types, lengths, areas, cross-sectional areas, so really quite a lot of information here. For us, we want to go with a line force, and we want to go ahead and put it in imperial kips per foot. I'm going to set the value at 45 kips per foot. I click OK. So how do we apply that parameter then? Well, I want to use a line load. And you can see here that my quick tools up here, my new member load is grayed out. That's because I don't have any members anymore in this particular model. But I can go ahead and apply a new line load. So the program tells me before I can apply a line load that I don't have any load cases defined. You know, is this dead load? Is this live load? So the program needs to know where do I attribute this load. So we're just going to go ahead and call this first one design load. I'm going to deactivate the self-weight, and we're going to assume that self-weight, all of our load combination factors, everything is included in this single load case design load. So if I click OK, then the program comes up with the new line load. And you can see here, if I go through each type, I mean, it's fairly self-explanatory, and the nice thing is that as I'm clicking on the different options, my little picture down here is updating, telling me, you know, where exactly my load is going to be applied in terms of my axes and my model. We'll leave this in the ZL direction, but we need to define the magnitude. So you'll see here this little button in our variable box, and we have the option for a calculator or edit formulas. And here you can see that parameter that we typed in. So if I type in a negative, double click on my design load, we can see the negative 45 kips per foot. So basically, we just use a variable to define it as our load magnitude. If I hit the checkbox, you can see this little yellow triangle over here, and that's telling me that I'm using parameters in the model to define my magnitude. I click OK, and then I can go ahead and click on that single line. Now, you'll see the 45 kips per foot here. If I go back into my parameters down here in my toolbar, you'll see that if I go ahead and change this now to 60 kips per foot, I click OK, the model is automatically updated. So parameters can be very useful for when you have, you're changing your loads a lot, or maybe you have a lot of structures that are of the same, very close to the same geometry, but you just want to slightly modify. Well, rather than going through and changing everything, you can actually incorporate these parameters directly into the program. Okay, so now that we are done with our loading, the last thing we want to take a look at is our FE mesh. And again, I think this is one of the very strong points of our program. With some other software, you need to sit there and draw all of your finite elements, whether those are plates or elements themselves or surfaces, and then you need to submesh and you need to make sure that they tie into loads correctly, that they're tying into members, and to me, that's just a lot of time spent trying to do a finite element analysis. So I just want to show you guys here that if we go to calculate and we go to our FE mesh settings, here are all of our criteria for determining our finite element mesh, and this is for automatic generation. The target length of our finite element is, the default is set to 1 foot, and 1 foot might be okay when you have a huge model, maybe some concrete slabs, and that would be fine. But for our case, we're kind of on a smaller magnitude here, so I want to go with something more like 0.2 feet. The other thing I want to point out is the shape of the finite elements. So you do have the option over here to choose quadrangles only, triangles only, or triangles and quadrangles. And what we found through a lot of testing is that this actually gives us the best results. A lot of people think that triangles are not good for finite element meshing, but in reality, this seems to be the best option. But you certainly can choose one of these other options if you'd like. And the thing to go along with that is that we do have another criteria here to choose squares where possible, and the default is to leave that checked. And then there's triangles for membranes. We don't have any membrane surfaces here, so that's irrelevant. The maximum ratio of FE rectangular diagonals. So you can see that the default is 1.8, and what that is the program is taking the dimensions of the rectangular finite element and making sure it doesn't exceed this 1.8 ratio. If it does, then it's going to go ahead and generate triangular elements out of that. You certainly can adjust this ratio if you'd like. And then we will go ahead and choose this option, regenerate FE mesh. All that this means is that if I'm ever in this global FE mesh settings and I click OK, it's going to automatically generate my FE mesh. So here you can see that the FE mesh was automatically created. No need to worry about tying it into these loads, tying them into adjacent surfaces. Everything is automatically done. Now, if we zoom in here and we take a look at this flange, for instance, you'll see that there's only 2 finite elements across the width. That's not ideal. Ideal would probably be more something like 4 to 6 elements to really give us an accurate analysis. So the option that we have is we can just double click on our surface to edit it, and you'll notice here that we have another option called FE mesh. We can actually choose to do an FE mesh refinement on this surface. So if I click available, you can see that my surface is the only option available here. I can set my target FE length to 0.02, sorry, 0.05. And now if I click OK, and I go back up to calculate, generate FE mesh, then the program has created much smaller elements, but only on this surface. So you have the ability to refine your FE mesh on individual surfaces. So that's quite nice, and you'll notice too that it transitions back into the global setting of 0.2 feet for both adjacent surfaces. For our case today, I'm going to go ahead and leave it as the 2 elements across the width, and that's just for solution purposes, just to speed things up a little bit. So I can go ahead and generate my FE mesh. So with that said, I think that we can go ahead and run an analysis in RFEM. Now the only thing I need to do, I already have my load case defined, so I can solve for my single load case by just clicking on show results. It's telling me they're not found, so should it start the calculation? I click yes, and our calculation is shown here. And like I said, the results comes up in the project navigator down here in the corner. We now have more tables for our results as well. Maybe we want to start off with our global deformations. Typical of a cantilever type structure, we have applied load at the end, so this is probably what we would expect to see. We take a look at our Y deflections. You can see it's set at 0.002, very small. Again, what we'd expect because we put all of those nodal supports in the Y translation direction. Maybe now we want to take a look at our surfaces. And so over here in my results project navigator, I just click on my surfaces, and then I have the ability to take a look at all these different results graphically. If we start with some of our moments for these finite elements, you can see here that everything is symmetric. And that's exactly what we should expect. If things were not symmetric, then we probably did something wrong with our modeling. We can also take a look at our normal forces in the Y direction. And judging by these contours, we can see that blue here is in compression and red and orange are in tension. Again, that's exactly what we would expect. Now maybe we are interested more in the stresses. So we can go ahead and view these in our project navigator. Maybe we take a look at our positive X stresses, our positive Y stresses. So again, this is why I really emphasize that you have to take care of where your local axes are pointing. If they're in every which way, you can understand that the positive Y stresses wouldn't really mean anything in this situation because they're not relevant to each other. We have our shear stresses, we have principal stresses. Probably what we're most interested in is our von Mises stresses. So that is our option down here. Now, if I take a look, most of my structure looks okay, but then I zoom into this point here, and you can see that we have some extremely high stresses, 105 KSI. And this seems to be a pretty important critical point here. But although I can see these stress values, the question is, how much am I over my limit stresses? So this is where our add-on module comes into play. If I go back to my data project navigator, and if you're familiar with RFEM, you'll know that this is where all of our add-on modules are, and it's quite the extensive list. This is for all of our different materials, all of our different codes. So we have the option to right-click on any of these add-on modules and choose them to be our favorite. And by clicking the favorite, it will go ahead and move those up to the top of this list here. And then I can just go ahead and double-click to launch this add-on module. And you can see that by an add-on module, it's nothing more than a dialog box still within RFEM. So I don't have to remodel anything. I don't have to think about the loads that I've applied or anything else. But rather, it will take the information from RFEM already, and then we further define some information based on this particular add-on module. We always work from top to bottom in these add-on modules, and then the actual criteria will be in this larger box here of what we need to go ahead and enter in. You can see here that it's asking us, okay, which surfaces do we want to go ahead and design? We can individually define surfaces, we can create new cases for each individual surface, or we can just go ahead and click all. And so we have surfaces 1 through 12 selected. Now the program's asking us, what do we want to use for our ultimate limit state? It will automatically choose our only load case that we have created, which is our design load. For serviceability limit state, for things like deflections, we could certainly choose this load case as well. Looking at materials, you can see that we have 2 materials in this model defined. Concrete is red. That's because it is an invalid material in a steel surfaces add-on module. The program knows, okay, I don't know how to use concrete material to do a steel stress analysis. Steel A992, though, if we click on that, this will give us all of our properties for this particular material. For our thicknesses less than 4 inches, it tells us that our yield strength is 50 KSI, ultimate strength is 65. If you had something over 4 inches, the program would have more criteria here to give you a different yield strength and ultimate strength. Okay, so lastly, we can go to our surfaces listed here. So here's surface 1 through 12 laid out. The thicknesses are all listed here. And we also have the option to optimize. This is pretty prevalent in a lot of our add-on modules for code checks and things like that. If I click on this, and let's say I know that I need to add a web plate in. We have extremely high stresses, and the web right now that I have just won't cut it. So I want to go ahead and add on this web plate, but I don't know what the thickness is. Well, I can actually set my limits of a minimum and maximum and how much I want to increase the increment by to go ahead and see what my ideal thickness will be. There's also the setting here to go ahead and choose your max available stress ratio. The default is set as 1.0. When we're looking at something more in design, probably 0.8, 0.9, something like that is more realistic in design. For us, though, we'll just go ahead and keep 1.0. If we click on the details button, this just gives us a little bit more information. And again, you can see that we don't have to sift through all this information if we don't want to, but it's kind of hidden here if you want to get into the real details of things. It's asking us what stresses to calculate. Right now the default is a shear stress, some principal stresses, and then of course our equivalent stresses, which are probably most important. What do we want to calculate these stresses according to? Default is von Mises, which we'll go ahead and use today, but we have some others, Tresca, Rankine, St. Benoit, so you can change those around if you'd like. Serviceability. Here we can set our deflection ratios. If deflection was a concern in your solution and you really want to find out if you're exceeding these ratios, well, here you can go ahead and set them. And then again, we use that serviceability load case that I showed you under general data to choose the load case we want to compare these to. And lastly, under options, I'll breeze over some of this stuff, but a couple of things I want to point out. The distribution of internal forces, I'll get into this into detail later on in the PowerPoint. Results in FE mesh points versus grid points, I'll show you that in just a minute, but for right now we leave it on FE mesh points. As I just mentioned when we were optimizing the thickness, here is our max level stress ratio. We can go ahead and change it in this window as well. Again, for design, maybe something more like 0.8, 0.9 is more realistic. So I think that we can go ahead and run our calculation. So you can see that rather quick, the program came up with our stress ratio. It gives us our stresses by load case, our stresses by material, our stresses by surface. So a lot of different options on how to actually view these. Our stress ratio is nothing more than our existing stress over our limit, which is 50 KSI. That's based on the A992 material. We can see down here we have a sad face because our ratio is greater than 1. And we can view this graphically here. And you'll notice that I'm now in this drop-down box called RF steel. So we have our original design load case, but now we're in the add-on module RF steel. I have a little bit different options here under my results tree. One of them is stress ratio, and like I said, we're probably most interested in these equivalent max. Now, if I zoom into our critical point, you know, this is where we're seeing the 2.11 ratio. So we can really see that this area is something of a concern. Obviously, 2.11 is not okay, so we'll need to address that. Now, the other thing that I showed you is that back in the details button, and now it's available here, we have FE mesh points versus grid points. So like I said, the options now are FE mesh points. And if I go down here at the very bottom, and then I can go ahead and view my values on the surface. And here we can see that if we click on FE mesh points, and one second. Well, it doesn't seem to be turning on, but that's okay. Okay, there we go. So if we zoom in, then we will see that these values are displayed at every FE mesh point. So that's what I wanted to point out. This is a rather small system, so I mean, although it seems a little bit overwhelming, if you did want to take a look at these, that is possible. RF steel surfaces allows you to go ahead and choose grid points as well. If I click this, it tells me I need to clear my results. And you'll notice that we have slightly different results here. I'll tell you the reason why. If we go back to the graphics and we turn off our values, what the program has, if we go ahead and double click on a surface, then there's another option here called grid. And within each surface, we can actually set a particular grid. And you can see the default is set at 1 foot. You can change it to Cartesian to polar. You can customize it. So you really have a lot of options here. The question is, why do we have this grid? Well, we can actually view the results on the grid rather than every FE mesh point. So I need to go ahead and recalculate, and I'm showing my RF steel surfaces. I'm set at grid points here. And again, if I go down to my values on my surfaces, I have the option here of to go ahead and view them on grid points. And you can see that we have a lot fewer results here. So for our example here, this isn't ideal only because we have such a small system. But if you had something like a huge slab and you don't want to view every FE mesh point, then you want to go ahead and view them as a grid set at every 1 foot or whatever you would like. So that is the point of the FE mesh versus the grid. Okay, so we are at a fairly high stress ratio here, 2.11. So this is where we want to jump into a plastic analysis. If we go to our tables down here and go back to our materials, we see that we have our concrete defined, which is not applicable to this particular model, it's just default. And then we have steel A992. If we take a look at the material model, we have isotropic linear elastic. And if I use my drop down, I have all of my different material model types here. As I mentioned, I think the Project Navigator is easiest to work with, only because I can go here to my data. This is all of my data input for my model. And I can see here I have a tree for materials. All I need to do is to right click on my steel A992 and click edit. Now we can see here our material models are also displayed in this drop down. And with RFEM itself, if you were to purchase just RFEM, this will come with isotropic linear elastic. This is the same stiffness in every direction. It's a linear elastic material. It also comes with orthotropic elastic 2D. This will allow you to define 2 different stiffnesses in 2 different directions for a surface element. It's still linear elastic material though. Now, what the add-on module RF MAT and L does is it will go ahead and release all of these other options. So that's nonlinear materials. Isotropic nonlinear elastic 1D, this is for member type elements. It will allow you to go ahead and set a yield strength for both tension and compression. It's still an elastic material though. And you can see here, and this is the case for all of these different models, we have a bilinear where we can take into account strain hardening, or we have a diagram where we can actually go ahead and define the stress strain diagram ourselves and take into account tearing and yielding. So again, you can really get into detail here. Looking at some of these others, isotropic plastic 1D, this is for plastic analysis for 1D type elements. Nonlinear elastic, this is going to be different in tension and compression for our surface and solid elements. Isotropic plastic 2D, 3D is what we'll actually be in today. Orthotropic elastic 3D, this will allow for 3 different stiffnesses in 3 different directions. It is still linear elastic material. Orthotropic plastic 2D and 3D, this will allow you to go ahead and define those plastic materials, different stiffnesses for both surfaces, and 3D is for solids. Now, isotropic thermal elastic, this is interesting if you have a very big temperature variation for your material. Here you can actually define the different temperatures and how your modulus of elasticity is affected by those different temperatures, as well as some of the other important variables here. So this is important for maybe steel design. Again, if you have a lot of different temperature variation, you can go ahead and use this particular material model. And then we have isotropic masonry 2D. This is for surface elements, and it's for masonry. And basically what this is telling us is that in flexure, we'll have a little bit of stiffness. In compression, we'll have stiffness, but in tension, we will not have any stiffness. So like I said, for our case, we'll go with isotropic plastic 2D, 3D. And up pops our dialog box. We're going to stick with the basic. Yield strength 50 KSI. This comes from steel A992, and then it's asking us which strain hypothesis. We will just stay with the von Mises. I click OK. I click OK. It's telling me my results will be cleared. Yes, that's fine. And now you can see that because I'm selected here in this in the table down here, it's steel A992, all of my members that utilize that material are also selected. So keep that in mind that the tables are synchronized with everything in the graphic view that if I click on something down here, it will be selected up in the model. So that's very user-friendly. You can see here that now we have isotropic plastic 2D, 3D. So let's go ahead and go back to our design load and run a plastic analysis. This will take a split second longer, only because we're running a nonlinear material, but I think you'll see that it solves rather quickly. Okay, so same type of view here, but maybe our stresses have changed a little bit. We're currently viewing the von Mises stresses. We zoom in here, we still have this critical point. And I'm looking at my values here, and I see that I'm at 66 KSI. And you would think with a plastic analysis, I shouldn't be exceeding 50 KSI. So we obviously have an issue here. Why am I exceeding that 50 KSI for a plastic analysis? And this is where I want to jump back into the PowerPoint. Actually, first, let me show you something. So this all just depends on how we're viewing our contours and how we're viewing our results. And this is a very important point. Along with the local axes topic, this one is very important as well because you can really interpret your results wrong if you don't know what you're doing. So if we go to our display in the Project Navigator, which again just controls what we're viewing in this graphic viewport here, there's an option under Results, and then I have Surfaces, and then Distribution of Internal Forces and Stresses. Now the default is continuous within surfaces, but we have a few other options here, constant on elements, non-continuous, continuous within surfaces, and continuous total. I won't touch on continuously by groups today. So this just means how are we viewing these forces and stresses graphically with all these different contours and such. And now we'll go ahead and jump into the PowerPoint. I want to explain these four options just in a little bit more detail because again, it's very important on how you view your results. And I think, again, this is not just important for our software, RFEM, but probably for most other software as well. The first option is constant on elements, and what this does is it will actually average the value at every FE node. So this is a single FE node here, and it's going to take the four corner points for this FE node, it's going to average them, and then it's going to place the results in the middle of the FE element. You'll notice that we do not have any contours here. Each FE element is actually colored in its own cell. This is ideal for plastic design. And so this is probably what we'll want to refer to. And with plastic design, what the program does is it'll go ahead and attribute the applied load to all of our FE elements. Now, if an FE element experiences any stress higher than 50 KSI, the program automatically recognizes that. It will reduce the stiffness for that single element so that we're not exceeding 50 KSI, and then the load is distributed to adjacent elements. Now, if one of these adjacent elements, same thing, if the stress exceeds 50 KSI, the stiffness is reduced, and the load is then further distributed to the other adjacent elements. And this continues on until we have a plastic effect for many of our elements, and the load is fully distributed. Looking at our other option here, non-continuous, this was the second option we could choose from. This is where our results from the displacements and rotations of every FE node are calculated. And you can see here that there is a corner value at each element, and there's a little dotted line that points to which FE node this actually belongs to. It's discontinuous distribution, so you can see here we don't have any contours between the different elements. We might have some contours within the same element, but we don't relate them all together. And realistically, this is not efficient. You know, there's really no way to interpret these results. So that's why we came up with these other distribution types. Here is continuous within surfaces and solids. And this is what our program is set to right now. This will average the values at the four corners of every FEM element. And it will go ahead and place that at the actual FE element. There will be a smoothing algorithm used between each element. But one thing to notice here is that I have one surface here on the left and I have one surface here on the right. There is not smoothing between the two adjacent surfaces, so there's an actual boundary there. Now the difference is with continuous total, exact same thing, the average value at the four corners. There will be smoothing between each element, but will also smooth between adjacent surfaces. So it's really up to you as the engineer to decide, okay, well, I have stress distribution between these two surfaces, or rather, should I have a boundary between them? So that's why I wanted to explain this a little bit more in depth, because for a plastic analysis, as I explained, we need to choose constant on elements. Now when I take a look, I'm below my 50 KSI. Now, as I mentioned before, this probably isn't an ideal mesh. It's rather big, especially for our critical point here. What I want to do is I want to go ahead and refine this mesh a little bit. So what I could do is I could take a global setting and reduce the mesh for every single element in the program, but that's going to really slow down my solution time. So if I zoom in here and I select this node right at the corner of all this intersection, I right click, there's an option for FE mesh refinement. I can choose new and go ahead and create a new FE mesh refinement. Now I have two options for a node. I can do either a circular or rectangular. I'll go ahead and choose a circular here, and maybe I'll set my radius at 0.5 feet, so 6 inches. My inner, I want it to be 0.05, and my outer 0.2 is fine because that'll transition nicely to our global setting. Now if I click OK, it's telling me, do I want to clear my results? That's fine. And then I zoom out, I can actually see this FE mesh refinement. That's what this symbol is indicating here. Again, just like the nodal supports, you have the ability to turn those on or off if they do seem to get in your way. Now if I go to calculate and generate FE mesh, and I zoom in here, well, I can see now that I have a much finer mesh at this critical point, but again, it transitions right back into my global setting of 0.2 feet. So I don't need to worry about any of that manually, but the program automatically does that. So now I can go ahead and go back to my design load case, and if I run an analysis again, and again, maybe a little bit longer because we have a little bit of a finer mesh here, but it's still very quick considering that we're doing a plastic analysis. Okay, so now we can see if we go ahead and look at our critical area and we're looking at our von Mises stresses, we're right below 50 KSI. This is exactly what we'd expect. You know, some of these elements are in the full plastic state. And maybe we want to know, okay, well, these contours are nice, but maybe we want to know which elements really have reached that plastic yield. So there's an option here under our results called criteria. And what criteria will show us is actually which elements have fully yielded. So I can zoom in here and you can see the ratio of 1.0. Well, these are my elements that have fully yielded. I can also take a look at my design ratio, and I had changed this previously. Let me show you something here. Our design ratio is between 0.01 and 1 for the plastic state. maybe I want to refine this a little bit because I'm most interested in this critical point. Well, with all of these panel options, all you need to do is just to double click on it. Maybe I set my lower limit to 0.9 and then I leave my upper limit at 1. If I just hit fill, the program will automatically interpolate all of these. I click OK. And now we can see we have a little bit more of a refined view for our contours. If we go back to RF steel surfaces, we want to go ahead and go to add-on modules, current module. Keep in mind here that under details, if we were to do anything with our RF steel, we also want to change this constant on elements. The RFEM global settings are not affected in this particular module. So we hit OK, and just to keep in mind, for RF steel surfaces in any of the modules, I don't necessarily need to go into the module to run it, but I can just go ahead and start the results here. And the program showing me my stress ratio, which is not exceeding 1 now. So with a plastic analysis, this is exactly, again, what we would expect. Okay, so what we want to do now is to go back to the PowerPoint and kind of sum up here after our plastic analysis. We want to show our imperfections. And I quickly wanted to address this because this is related to the code. And the code in the AISC 360 Chapter C, the direct analysis method, tells us that we have to account for imperfections. Now, a lot of engineers will account for imperfections with notional loads. This is fine maybe on more of a global level, but for us, we're doing a finite element analysis of a connection here. So notional loads might not be completely applicable. So C2.2a in the code says that we can actually directly model these imperfections. Here we'll want to anticipate and scale our buckling modes, and then after we scale it and we create an imperfection, we actually want to include this imperfection in the analysis. I also went ahead and referenced the Design Guide 25 here for web tapered members. This also tells us that the engineer must determine the lowest eigenvalue buckling mode. Pretty similar to a lot of the other references in A.3 in the Design Guide 25, it really only addresses member or global buckling loads. So there isn't a whole lot of information, there isn't a whole lot of information on local buckling modes. So when we take a look at the AISC 360 on how to scale these, it references the AISC Code of Standard Practice. The Code of Standard Practice tells us that misalignment must be less than L over 500. And L is not the distance between, maybe our simply supported beam or beam length. It's actually the distance between working points. So we'll get into this in just a minute. I also found the reference from Kim and Lee, Engineering Structures, Volume 24. They suggest on the local level to use the max of our flange width divided by 150 or our depth divided by 150. I've also seen people use a percentage of the plate thickness. So it's kind of up to you on this local level how you want to scale. For us, we're going to go ahead and stick with the AISC Code of Standard Practice. Now, that was kind of a lot of information, so I want to show you exactly how we can model an imperfection. As I said, the code tells us that we do have to consider them. So what we're going to do is go into our Data Project Navigator and utilize our add-on module RF-STABILITY. Now, you'll notice RF-STABILITY looks very similar to our other add-on module, and that's the benefit. Most of these add-on modules look exactly the same, so it's not going to be a crazy module that pops up that you have never seen before. They all look pretty similar. It's asking us the number of lowest eigenvalues to calculate. The default is 4. That's fine for this example. Now it's asking us, okay, well, where do we want to import these forces from? Well, fortunate for us, we only have one design load case defined, so we'll leave that selected, of course. Which stability analysis do we want to use? We have the eigenvalue analysis, which is basically a linear type analysis. Again, for our example, this is fine. The other option we have is increase load until structure failure. This is more of a nonlinear analysis. So we can actually define the different load increments. This is more for taking into account nonlinear supports, nonlinear materials, cables. The program will actually apply this load in load increments, and after each increment will take into account different stiffnesses, different load distributions. So a little bit more complex here. For us, again, we're sticking with the eigenvalue analysis. Eigenvalue method. The method by Lankos is for small to medium-sized systems. This is fine for our particular model. You know, it's very small. The larger model that you have, the more you might want to move down this list. But keep in mind that your solve time, of course, does increase as you, again, move further down this list. So now we can go ahead and click calculate, and the program is going to find the local buckling modes for our applied load. I'm going to quickly exit out of this, and the reason why is I just want to spin this around and show this to you guys of what exactly is happening here. Going back into RF stability, here are my 4 eigenvalues that were calculated, and this is only based on that single point load or line load that we placed at the end of the structure. You can see the eigenvalue number 1, it's a local buckling of the web. Number 2, same local buckling of the web in a different location. 3, it looks like the lower flange, and number 4, maybe a little bit higher up on the flange. And we're also given the critical load factor. What this means is that this is the number, this is the factor that we can multiply this applied design load, you know, this line load that we apply down here by 2.97 before we're going to see some type of behavior such as this. And as the code called for, we need to consider the lowest eigenvalue. So for us, this is going to be eigenvalue number 1. You can see here in our pictures, we have an eigenvector listed. There are no units, there is no direction, it's an eigenmode. So in order to create an imperfection, we need to go ahead and scale this by some particular length and direction. And that's where we will go ahead and get into our other add-on module called RF-IMP, and this is generation of imperfections. Again, looks very similar to the other add-on modules. Here it's asking us, okay, do we want to generate an imperfection based on a deformation from a load case or a load combination? But instead we're going to use a buckling mode from RF stability. So it's tying those 2 modules together. We only have 1 case, and we're going to solve for number 1. And now we need to go ahead and scale it. And this is where I said, you know, it gets a little bit tricky into how you interpolate on the local level. For me, I'm going to go ahead and I'm going to exit out of this. I'll just put an arbitrary 1 in there. I'm going to exit out of this, and what I want to show you guys is I'm going to use the, back to the PowerPoint here, I'm going to use the AISC Code of Standard Practice that misalignment has to be less than L over 500. So going back to this model here, if I change my work plane and I set my origin here, I just want to go ahead and measure my work points, so to speak, of my buckling shape. And so if I measure from here down to here, I'm getting a value of about 4.68. So for me, I'm going to kind of translate this into my misalignment cannot be more than about 5 feet. We'll just round up over 500. So if I go back into RF-IMP down here, and I can go to current module, I'm going to scale this by the 5 feet divided by 500, which comes out to 0.12 inches. Now, the other criteria where I said the flange width divided by 150 or the depth divided by 150, I think we get about 0.13. So we're all within the same realm here. I'm going to also change this to a negative, and the reason why I'll show you in just a minute. If we click generate, then you'll notice here that now I have all these FE mesh point coordinates and the deformations in inches. I can go ahead and see my graphics, and the reason why I put a negative is just so that I could switch this around. It doesn't matter, it's an eigenmode, so you can put whatever direction you'd like it to be in, but now you can see that our deformations are defined at that 0.12 inches. Now, lastly, we want to, again, the code calls for to incorporate this imperfection back into our analysis. So how do we do this? Back in our data tree, I'm going to collapse my model data, and now I have load cases here. And I have design load. And all I need to do is to right-click and copy my load case. It's asking me what do I want to call this one. I'll just call it design load plus imp for imperfections. If I double click on this, it brings me back to this familiar load cases, and I can go ahead here and go to my calculation parameters, and then I see here I can click on extra options. Under extra options, I can activate a generated imperfection from my add-on module. I can do that. I only have one case that I solve for, so again, we'll use that one. Calculation parameters. The default for load cases is geometrically linear analysis. Default for load combinations under the second tab is p-delta analysis. We also have a large deformation analysis. This is typically used to take into account both longitudinal and transverse forces. Also, our stiffness matrix will be changing for every iteration. So because we have this available, I'm going to go ahead and select this option here. I click OK, and then I'm going to run my design load once more. It's telling me my results aren't bound. Should I start the calculation? And again, takes a split second longer. It's now a large deformation. It is plastic analysis, so we're not using linear materials anymore. But considering those circumstances, I think it's rather quick. So maybe what we first want to take a look at are our deformations. So if we take a look here, this is the global deformations. Again, exactly what we would expect for a cantilever type structure. But let's take a look at the Y deformations. And here we can see that that imperfection was taken into account in our analysis. I can use my scale factor here to go ahead and increase this to really see what's going on with the web. And we took that imperfection into account, and we can see this by this small deformation within the Y direction. Again, we have the option to take a look at our surfaces. If we go down to our von Mises surfaces, we still have our critical point here. And sorry, I'm looking at strains. We want to go ahead and take a look at stresses. There we go, and we're right under the 50 KSI. So that's exactly what we want for a plastic analysis. So essentially, that is how you would incorporate everything together. You know, more on a local level, we're incorporating these imperfections that the code calls for back into our analysis. I'm going to jump back into the PowerPoint, and we can go ahead and finish up here. So I know that we were in quite a few modules today. We were also in RFEM. So if you guys want to find out anything more about these add-on modules and RFEM itself, we certainly have more information on our website at dlubal.com. We have plenty of social media sites. For example, YouTube, we have a lot of older webinars there that might be beneficial for you to take a look at. Our email here in Philadelphia is info-us@dlubal.com, and our phone number is 267-702-2815 if you guys have any questions or concerns. I did want to go ahead and make note that we will have another webinar on May 26th at the same time, 2 p.m. Eastern. We're going to utilize Revit and RFEM integration. I know that a lot of engineers take into account both Revit, and they want to see a comparable solution to integrate with their structural analysis software. So keep on, you can go ahead and sign up through our website. It's under support and learning and webinars, but I will also go ahead and send out an email as well, maybe a week or so before that. If you guys are interested in PDH credit today, certainly send me an email at info-us@dlubal.com, and I will go ahead and issue that certificate for you. That's no problem at all. And with that, that sums up the webinar today. So I want to thank everyone for attending. Again, if you have any questions or concerns, feel free to reach out to us. And we hope to see you at the next webinar. Thank you.